In this video, we're going to take a look at how to calculate probabilities of binomial experiments, which will speed the process up from the last video where we were doing them all by hand, but this does come with its own challenges. In particular, the graphing calculator has two different binomial functions that we can use. So if we are talking about the probability where we have exactly x successes, so this is if I wanted exactly 2 successes out of 5 trials or however many. So I'm talking about one specific case. Then I'm going to use the function binomial PDF right here. N representing the number of trials, P is the probability of success, and then X would be our number of successes. And I'll show you how to find that on the graphing calculator in a minute. The directions are also in the text above this video. So the thing to remember is that we want this binomial PDF right here. If, on the other hand, I'm talking about a wide range of values, if I want to talk about the probability that I have less than or equal to x successes, and this is where it gets a little bit tricky, is that the graphing calculator will really only deal with this less than or equal to x successes. If I have greater than or equal to, or strictly less than, I'm going to have to get creative about how I write this or type this into my calculator. And we'll talk about how to do that in a couple of examples here. In those cases, I'm going to use the binomial CDF function, again using n, p, x, so n being the number of trials, p the probability of success, and x the number of successes. So let's continue on. We're going to look at the same example that we were working with at the end of the last video. It says, suppose that the probability that a student is admitted to an Ivy League school is about 17%. Suppose a group of 10 students apply to the school. So first thing I want to do in all of these problems, I should probably decide how many trials am I running and what's the probability of success, and perhaps what is a success. In this case, I'm going to define a success as, well, they are admitted to the school. I'm going to peek ahead and say, okay, well, they are admitted. So the probability of success we're going to say is P equal to 17% or 0.17. So my probability of success is 0.17, and I have 10 students that want to apply, so I have N equals 10 trials. So let's take a look at number 1 here. It says find the probability that exactly 2 of the students are admitted. So here we're talking about exactly one scenario where I have 2 students that are admitted. And if you need to, you can take a second, and this will be particularly helpful in the next problems that we look at. You could say, okay, list out the number of students admitted. And just think about, well, what does the sample space for this look like? What are the possible number of successes? Well, I could have 0 students admitted, 1 student admitted, 2, 3, 4, all the way up to a total of 10, because that's the number of students that I'm admitting, or that are applying, excuse me. So when I say exactly 2 of the students are admitted, we're looking at just this case and this case alone, where I have exactly k equals 2 successes. So that means I'm going to be using this binomial PDF function up here. So I like to write out the actual syntax of what you're going to tell the calculator, and this is particularly helpful if you have an old graphing calculator. We already know P is equal to 0.17 and N is equal to 10. But if I was going to write it out in this syntax, in this kind of way that I'm going to talk to the graphing calculator, I would say, okay, I want binom, we said PDF, because we have exactly one case. N is 10, so we're going to say 10, P is 0.17, and then the X, is the 2 in this case, the number of successes that I want. So we would say 2 right here. So this is going to be what I enter into the graphing calculator. Some newer graphing calculators will make it easier to use, and you'll see that coming up here. But if you have an older graphing calculator, this is what that text is going to look like. So let me hop over to my graphing calculator. We can show how to find that. So on my graphing calculator right here, I'm going to start by pressing second and then vars right here. This will take me to my distribution menu, and I'm going to have to scroll down quite a bit here. I'm going to have to scroll down until I see either binom PDF or binom CDF, depending on which I want. So options A or B. We said we wanted binom PDF, so we're going to choose option A. And if you have a newer graphing calculator, it will actually ask you for this information. It'll say, how many trials do you want? Well, we said 10 trials. The probability of success P is 0.17, and the X value is the number of successes that we want. So we want exactly 2 successes. And if we arrow down and go to paste and press enter, it'll automatically enter it in that same syntax that we wrote it out in just a second ago. Now, if you don't have a newer graphing calculator, if yours is a little bit older, like a TI-83 or something like that, that's still okay. You can still do this problem, but you will not see that menu. You'll see something like this where it says binom PDF, and you're going to have to enter in the information in that order that we just talked about in the last page. So you would start with the number of trials, which is 10, and then we'll use a comma to separate these. So comma P, which is the probability of success, 0.17, and then the number of successes that we want is 2, so we'll enter in 2. And then we can go ahead and press enter, and we should have the same probability that we had in the last example, 0.2929. So we'll round to 4 decimal places in these problems. Make sure you pay attention to the homework problems. It'll tell you how many decimal places, but we'll do 4 just to be safe. 0.2929. So let me hop back. My probability here is 0.2929. If you're going to use this method on quizzes and exams, I would really like to see this binom PDF syntax written on your paper. And the reason for that is if you don't have that, and perhaps you make a typo or maybe you use the wrong number, whatever it is, and if this number that you give me is wrong and you have no other work, I cannot give you any partial credit. But if you show me, hey, this is exactly what I typed into the graphing calculator and maybe you made a mistake, let's say just like with your probability of success, I can say, okay, well, they were using the right function, they were using PDF, they had the right N and the right number of successes, they only had the right or the wrong p-value. You know, I can give you partial credit on that. So that's certainly to your benefit to make sure that you write that out. Let's take a look at another example here. In number 2, this is the same example that we looked at in the last video. Find the probability that at least 2 of the students are admitted. So again, here we have at least 2, meaning we're going to have more than one outcome that we want to think about. We're going to have more than one case that we need to consider. Now, in the last video, we had to get creative. We used the complement, and we're probably still going to use that here. But we ended up having to do our binomial probability experiment, or excuse me, our binomial probability formula multiple times. And what's nice about the graphing calculator is once you figure out how to talk to it, we're only going to have to do one thing. So I think it's extremely helpful, and I'm going to come up here and copy and paste this. I think it's helpful to think about the sample space for this experiment. When we think about these multiple outcome cases, I'm going to think about the number of students admitted. So when we say the number of students admitted is at least 2, so first thing I want to ask is, well, is 2 at least 2? Yes, it is. 2 is at least 2, and when we say at least 2, what we really mean is 2 or more. So we have 2 or more over here. So it could be 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10. Just like that last video, I could go and I could use binom PDF for every single one of these. I'd have to do one where x is equal to 2, one where x is equal to 3, one where x is equal to 4, and so on and so forth. And that would be a huge pain in the butt to do. In these cases where I have multiple outcomes, I want to try and use that CDF function. It's usually going to speed this process up. Now, if I were to look at these values over here, these are all x values that are greater than or equal to 2. I'm going to try and use these greater than or less than signs. The graphing calculator won't do anything with this greater than or equal to. Remember, if we scroll back up and look at the CDF function, CDF only does this greater than or, excuse me, less than or equal to. So we have to find a way to write that with a less than or equal to, in which case we would say, okay, well, that's really just the complement of what we want. We could say, okay, 0 or 1, this is the complement of what we want. So, okay, we know how to deal with that. And these values are less than or equal to, and I'm going to pick the largest number that I have right here, is 1. These numbers are all less than or equal to 1. 0 and 1 are both less than or equal to 1. So probably the fastest way to do this problem is to say, okay, well, I'm going to start off with binomial CDF. I'm going to say, okay, I want to talk about binomial CDF. My n, my number of trials, that is still 10. The probability of success is still 0.17. That hasn't changed. The x value, the number of successes that I want to talk about, is this number right here. It's this 1. So we're going to go ahead and enter this into the graphing calculator, but we're going to keep in mind this actually isn't quite what we want. We want the complement of this. So I want, let me hop back over here real quick, to go into my graphing calculator, and I'm going to press second vars to bring up my distribution menu, and I'm going to scroll down until I see binomial CDF, and it should be option B right here. The menu will look basically exactly the same. It'll ask for the number of trials, which is still 10. The p-value, the probability of success, is 0.17, we said, and the x value was, in this case, 1. So we'll go down, we'll paste it, we should hit enter, and we end up with 0.4729. That 5 is going to make that 29 round up, so that would be 4730. So let me hop back over here. So 0.4730. But remember, that's not actually what I want. This is the complement. That's not quite what I want. I still need to take this probability and subtract it from 1. So to finish this problem up, I want 1 minus 0.4730, and we can hop back to the graphing calculator to find out what that's going to look like. And if I scroll, 1 minus 0.4730, I should end up with 0.527. So we want to be careful, and this will take some practice here. We want to get some practice working with this CDF function because it does take some setup. Once you get it set up, yes, it is something you can just plug into the calculator, and it'll do all the heavy calculation for you. But you need to take a second to figure out, okay, how can I write this in a less than or equal to statement, which can be tricky when you're working with greater than or equal to statements. It takes some practice. Let's take a look at one more in this video. Number 3 says, find the probability that at most 4 students are admitted. So again, I want to think about the sample space. I'm just going to copy and paste this down here so that we have it in front of us. So when we say at most 4 students, 4 is the most we can have. We can't have more than 4. So you could have 4. So 4 is going to be included in this. And if we say at most 4, well, we can't have more than 4, but we could have less than 4. So you could have 3, you could have 2, you could have 1, you could have 0. We're looking at this set right here. And again, I want to try to write this in a less than or equal to statement. In this case, it works out quite nicely because all of these numbers are less than or equal to 4 right here. I'm going to just take the largest number in this particular set. So they're all less than or equal to 4. And in this example, I don't have to do anything with the complement here because I'm already starting off with this less than or equal to statement. I needed to in the last example because I was dealing with this greater than or equal to. So anytime you're working with greater than or equal to, you're going to have to use the complement if you want to use the graphing calculator. So the fastest way to do this problem is to say, okay, I want binomial CDF. N is still the number of trials, that's still 10. The probability of success is still 0.17, and the number of successes that I want is 4. So I'm going to go ahead and type this into my calculator. So one last time, hopping back over here. I'm going to clear this out. Let's go back into my distribution menu, second vars. We're going to scroll down to binomial CDF, which should be option B. And honestly, if you're working with multiple parts of the same problem, it's nice. It will save the number of trials and the probability of success. We just need to change our X value. We said that was going to be 4 here. So I'm going to go down, paste it. We should have 0.9832 if I round to 4 decimal places. So 0.9832. 0.9832. There is my probability. So these binom PDF and binomial CDF functions really do speed up the process. One thing I will mention is if you're extremely stubborn and you want to use that PDF function for everything, you certainly could. You could say, I want to do binom PDF, and say, okay, I want to use 10 trials and probability of success is 0.7, but I'd have to do all of these numbers over here, 0, 1, 2, 3, 4. So I'd have to say, okay, I'd have to start with 0. So I'll say 0 successes, and then I do binom PDF with 1 success, and binomial PDF 2 successes, and binomial PDF 3 successes, and binomial PDF 4 successes. And then once I have all these, I'm going to add all of them up. So you could technically do that for this problem, but it gets to be pretty tedious. And in this problem, okay, there's 0, 1, 2, 3, 4, so there's 5 cases that we would have to do. But if we had many, many cases, if I was running, say, like 100 trials, you can imagine a case where this is no longer feasible. You kind of have to rely on this CDF function right here. It will save you quite a bit of time. But see if you can take a second and at the beginning of your problem and write out that less than or equal to statement, because it does help a lot to write out the sample space and to try and get that less than or equal to statement so that we can use that in our binom CDF function.